Hi, and welcome to Library Seminars, an educational platform for the presentation of research and ideas in support of the National Oceanic and Atmospheric Administration's mission. My name is Lisa, and I am your host from NOAA Central Library. Today's library seminar is part of the 2021 Knauss Fellows Lunch and Learn series, a monthly webinar where Knauss Fellows showcase their own research. Caleb Taylor, a 2021 Knauss Fellow working with the United States Department of Transportation's Committee on the Marine Transportation System, will be our moderator today, and he will introduce our four speakers, each of whom will speak for 10 minutes about their research in a lightning round, which will be followed by a Q&A where the fellows will answer your questions. So before I hand the mic to Caleb, I have a few logistical tips to help you enjoy our presentation. If you're having trouble with the audio or visual components of GoToWebinar, please log out and rejoin us. This resets the software and resolves most technical issues. Our presentation is being recorded and will be available on the NOAA Central Library YouTube channel later today. I've put the link to the channel in the chat box. Also, all audience members are muted, but we do want to hear from you, so please ask questions. We encourage you to type them in the questions chat box located in the control panel throughout the presentation. Let us know to whom the question is addressed by indicating the name of the person you'd like to answer the question. And all questions will be answered at the very end of the four presentations. So with that last detail, let's get started. The mic is all yours, Caleb.
Yeah, thank you so much, Lisa. Really happy to be here. So again, kind of what she was saying, this is put on as a partnership through the NOAA Library, Central Library, and the Knauss Lunch and Learn Committee. So we're very excited about that, and we're very excited that you all are here today to learn a little bit about what some Knauss Fellows are doing, from citizen science to phosphorus, carbon, and even sea cucumbers. So get your lunches ready. It's going to be a fun ride. So first off, I will introduce Sandra Demberger. I actually met her through our Knauss kickball team, but she is the Coastal and Marine Resource Specialist with the Fish and Wildlife Services Coastal Program. And fun fact, today is actually her one-year thesis defense anniversary. So we're excited that she's able to join in and share a little bit about it on such a special day. And she also received her bachelor's degree from the University of Delaware and her master's from Villanova University. So please welcome Sandra. It's off to you. Thanks.
Awesome. You can see my screen. You can hear me. You can see me.
You look great.
Awesome. Love it. All right. So thank you for joining today. I'll talk a little bit about, well, I guess the title of my presentation is how much carbon is stored in the Plum Island Salt Marsh and what is that worth? So we're going to dive right on in. Here we go. With talking about what a salt marsh actually is. So they exist at the land-sea interface and flood twice daily with very salty water. So there's only, biologically, there's only a couple of plant species that are able to live in these pretty strenuous environments. However, your wildlife, there's tons of critters. We've got spiders, little hermit crabs like you can see in this picture here. All sorts of shorebirds rely on these systems, as well as a ton of different fish species. So these are really interesting dynamic systems. And from a geophysical standpoint, there's a very complex relationship between the suspended sediments and the vegetation. And that complex relationship relates to a distinct high marsh and low marsh area, which I will talk about a little bit later on. These systems are important to us because of their ecosystem services. They provide services like flood control, nursery habitat. Economically important fish species really rely on these for nursery habitat. But today I'll focus on carbon sequestration and storage. And this ecosystem service is sometimes overlooked. It's definitely gaining traction, but hopefully by the end of my presentation today, you'll see how valuable this ecosystem service is. So let's dive on in. So carbon in the atmosphere is, through CO2, that's something that we emit when we drive our cars, when we heat our homes. All sorts of anthropogenic activities put CO2 into our atmosphere. And so our salt marsh plants are able to take up that carbon, and that O2 obviously gets released back into the atmosphere. That's what we breathe. But that carbon gets stored in the plant matter. And so over time, as our plant matter, that biomass senesces and dies, and as we have our tides coming in, we have new suspended sediments coming in that settle on the marsh. And then over time, that carbon is buried in the marsh. We have new plants growing on top. And so over thousands and thousands of years, our marshes are accumulating really deep peat beneath the marsh surface. So really thick peat beneath there. And so when we're calculating our carbon stock, we're really addressing that carbon that's been stored there essentially over the lifetime of the marsh. So what kind of things are influencing our carbon being stored in our salt marsh? Well, we have local variations. We have variations between our high marsh and our low marsh, as I mentioned earlier. So the high marsh generally has a higher carbon content, and that's because it floods less frequently. It's sitting slightly higher in elevation. And because it floods less frequently, it gets less suspended sediment, and it causes that soil to be more organic or have a higher carbon content. Our lower marsh areas, on the other hand, have a much lower carbon content, and that's because they flood a lot more frequently, because they're lower in elevation in the marsh, and because they flood more frequently, they receive more suspended sediments, and therefore have a slightly lower carbon content compared to our higher marsh. And we also have variations through the depth of the marsh, and these types of things make it pretty challenging to estimate our carbon stock. So we're going to try and estimate the carbon stock today of a section of the Plum Island Salt Marsh. And Plum Island is located in northern Massachusetts, which is near the Parker River National Wildlife Refuge, for those of you familiar. And as a reminder, our two big questions for today are, how much carbon is stored in the salt marsh, and what is the monetary value of this carbon? So in order to do that, we're going to look at a pretty basic equation here. So our carbon stock is equal to the area times the carbon content times the depth. This is basically we're finding the volume of the marsh and then multiplying it by the carbon content. So let's dive right on it. So here we have our exact study area in this white box, as you can see here on the left side. And it's only about 9.2 square kilometers, so it is a pretty small area, but it'll definitely give us a good idea of how these analyses work and the impacts that the carbon has in these systems. So within this area, it's really important to identify those high marsh and low marsh areas because they accumulate carbon at different rates. So here in this map, we can see our higher marsh in that darker purple area, kind of around the outside, if you can see my mouse here. And then we have our lower marsh area right here around the channel and another little smidgen over here. So next, let's think about our carbon content. My team and I poked a handful of holes in the high marsh and low marsh areas and extracted soil cores up to 5 meters in depth, which is about the total depth of the marsh. And so this map shows where we extracted those cores. There's a couple in the high marsh areas, there's a couple in the low marsh areas, and the depth of those cores varied anywhere between 1 meter and 5 meters, as I mentioned. And so what we did is we schlepped those cores back to the lab to analyze them for our carbon content. And from this, we learned two things. First, we confirmed that the high marsh does in fact have a higher carbon content than the low marsh, so the literature I read was correct. That's good. And next, we learned that the deeper cores store more carbon, and this is due to that process that I mentioned at the beginning, where you have that relationship between the suspended sediment and the dead biomass over thousands and thousands of years. You have a very deep peat layer beneath the actual marsh, and so that's why your deeper marsh has a higher carbon content. And so next, let's think about that depth component. That's pretty much the trickiest part of this whole analysis because that requires poking a ton of holes in the marsh and figuring out that depth. Luckily, a previous study done by Kerwin et al. Back in 2011 essentially did this part of the project for me. And so you can see here on this map, each of these yellow dots is a depth point, a place where I have depth data, I should say. And so let's highlight here just a couple. Right here in this lower marsh area, we can see that these are around a meter and a half in depth, so your marsh depth, versus out here in your higher marsh areas, right here around the upland edge, we have nearly 4 meters depth of marsh, and here we have maybe 3.5 meters, or 350 centimeters. So you'll notice the depths in the low marsh areas are generally a little shallower versus the high marsh areas, which are generally a little bit deeper. So now that we have all three of these components, we can calculate our carbon stock. So here we have our total carbon stock. You'll notice that those deeper purples and dark blues are where we have our higher carbon, and those lighter areas are where we have our lower carbon. Those are associated with those lower marsh areas. So we have a total of 858,000 megagrams of carbon. So what does that actually mean? I think that's pretty challenging to wrap your heads around. Well, that's equivalent to 3.1 million megagrams of CO2. And okay, CO2 is a little bit more relatable. We know that's a greenhouse gas. But what does that really mean? Well, it's equivalent to the emissions that would result from the combustion of over 353 million gallons of gasoline. That is equivalent to taking over 667,000 cars off the road for 1 year. That's a ton of cars, a lot of cars, a lot of gas, a lot of carbon being stored. So what is the dollar value of this system? We can use something called the social cost of carbon. And this is something that's determined by economists. And most simply stated, the social cost of carbon is the monetary value of the total damages that we will endure with an extra 1 ton of CO2 added into our atmosphere. And this can get a little tricky. The word damages is an economic term here that refers to the economic impacts of climate change on things like agriculture, healthcare costs, energy use, those kinds of things. So an example might be that climate change is leading to warmer overall temperatures, and that may cause more heat stress and may decrease air pollution, may decrease air quality, leading to more pollution. And those kinds of things will lead to more hospitalizations, which has a greater economic impact on society. So those are the kinds of things that the social cost of carbon accounts for. And there's tons of debates by economists, politicians, all sorts of people on the exact value of our social cost of carbon. So for today's purposes and in the interest of time, we'll keep it simple and just use the value of $59.84 per megagrams of CO2. So when we multiply that by our carbon stock, we find that our little 9.2 square kilometer area of salt marsh is worth around $188 million. That's a lot of money. So if the carbon stored in this salt marsh was suddenly released out into the atmosphere, we would expect to endure around $188 million in economic impacts. And that's really quite significant for such a small portion of the marsh. Just imagine if this was scaled up across the entire United States to all the marshes. We're looking at over $300 billion in carbon being stored. That's billion with a B. That's a lot of carbon. So what does this really mean kind of for us here in this presentation and in general for practitioners? Well, first it means that there's a ton of carbon stored in our salt marshes, and that in and of itself is really quite impressive. But with climate change and accelerated sea level rise, our marshes are drowning and we're experiencing a lot of erosion in these areas. And this is causing that stored carbon that was stored, over thousands of years to be released back out into the oceans and the atmosphere, which, as you might guess, is not something that we want. And so I hope that more studies will be done like this in our coastal areas. And hopefully these studies can help advocate for marsh restoration and conservation projects and help get more funding for projects that'll make, our marshes stay happy and healthy. And so with that, I'd like to thank Villanova University and the Plum Island Long-Term Ecological Research Station for their funding support back when I did my master's. And thank you for listening. I think questions will be saved for the end. So with that, I'll hand it back over to Caleb. Thank you.
Yeah, thanks, Sandra. Great job. And like you, I hope that we do have some more studies similar to this across the country. It seems really important. And Lisa will be fielding questions at the end, so please feel free to type them into the chat as we move along, and we'll field them at the end. So up next, we have Rachel Johnson. Rachel is the 2021 Knauss Fellow in NOAA's National Ocean Service, and she's working on coastal resilience policy, very important. Prior to joining NOAA, she earned an MS degree in water resources management and environmental engineering from the University of Wisconsin-Madison, so degrees plural, rather. And she completed her undergraduate at Carleton College. Throughout her studies and her previous work, Rachel is focused on collaborating with local communities to understand and adapt to impacts of climate and land use change on freshwater resources. So with that, I'll give it off to her, and the title of her discussion or talk rather is Chasing Phosphorus, the Impacts of Past Land Use on Current Water Quality. So Rachel, off to you.
Awesome. Thank you very much, Caleb, for that introduction. Hoping you all can hear me just fine. So thank you. I'm glad to be here today with you all and to share about some of my research from my environmental engineering master's program. Next slide, please. Before I start, I want to acknowledge that my research area and the location that I'm speaking to you from today are on the ancestral unceded lands of the Ho-Chunk people, who have been stewards of these lands and waters since time immemorial. And if you're interested, I'd invite you to check out this website on the bottom left here, native-land.ca, to learn more about the lands that you live and work on. Next slide, please. So as Caleb said, I did grad school at the University of Wisconsin-Madison. And for those of you who've been to Madison, you may know that the campus sits on this beautiful lake. But as you can see in this photo, the lake is not always so nice. Like numerous other lakes and freshwater bodies across the country, it experiences nuisance and toxic algal blooms like these in the photo, which can smell, make people and animals sick, and lead to fish kills and dead zones. And this is something that I imagine many of you have some experience with. Next slide, please. So in freshwater bodies, the nutrient phosphorus, in addition to nitrogen, can trigger this poor water quality. When phosphorus gets into lakes, rivers, and streams, it essentially provides a source of food to aquatic plants. They can start to grow out of control, and then when they die off, they use up available oxygen, creating low oxygen conditions. And this process, called eutrophication, has major environmental impacts to fish and aquatic communities, as well as social and economic impacts to recreation, tourism, and drinking water supply. Next slide, please. And this phosphorus can originate from a variety of different sources. And these can be things like the atmosphere, human food products and waste, dog waste, and fertilizer applied to turf grass. And it can also originate from agricultural sources like fertilizer, livestock feed and supplements, manure, and pesticides. And how much each of these sources matter really depends on the specific watershed. And phosphorus from these sources in the watershed can get into streams, gutters, storm sewers, or tile drains, and then create problems for downstream water bodies. Next slide, please. Now, research in recent years has shown that it's not just the current or contemporary sources of phosphorus that are providing sources to water bodies. Next slide. But also this historical or legacy sources that may have been accumulating over decades. And this is especially true in watersheds that have long histories of intensive agriculture with row crops and livestock. And because phosphorus likes to stick to soil particles, over time it can accumulate within these watersheds based on land use and management practices. And it will stay in those locations until either the soil can't hold any more phosphorus, so it is released, or until the soil particles get moved by water. And then this can become a source of phosphorus to water bodies, even if the original source originated decades ago. And this is a really big challenge for watershed managers who need to be able to choose effective management practices and communicate reasonable timelines for water quality and improvement. And for my master's, I had the opportunity to work with a lake community in Wisconsin that's actually within the watershed of Lake Michigan. And this community was concerned about legacy phosphorus. Next slide, please. So Green Lake is the deepest inland lake in the state of Wisconsin at 236 feet. And for over 150 years, the lake has been a popular vacation destination, and the watershed has supported productive livestock and crop production. Over the same time period, though, there have been more and more signs of eutrophication in the lake. And despite spending millions of dollars on conservation practices in the watershed that were intended to prevent phosphorus from getting to the lake, water quality issues have persisted. So the Green Lake Association and related local county and state agencies wanted to know if there was a legacy phosphorus problem and what that could mean for lake management. So I looked to answer two major questions. One is how much phosphorus moved through this watershed over the past 40 years? And second, where is that legacy phosphorus most likely stored? Next slide, please. So I looked at this using a combination of lab work, field work, and modeling. I'm just going to skim through these methods so we can get to some of the more interesting things, but I'd be happy to answer any questions about these later. To get at that second question, where is phosphorus stored within the watershed? I took sediment cores, much like Sandra was actually describing, and also used previously collected cores as well as GIS data and some paleoecology methods to estimate how much phosphorus was stored in the sediments of the lake, as well as two major wetlands. And then to get at that first question of how much legacy phosphorus may have accumulated in the watershed, I chased down all the major pathways of how phosphorus enters and leaves the watershed, and then modeled 40 years of those flows using a mass balance, which is kind of like a checkbook where you take additions minus removals to estimate what was stored. And also in order to do this, I reconstructed historical land cover populations of humans and livestock in the watershed using census data and agricultural census data and GIS spatial data. And then I found appropriate estimates for phosphorus content for different flows using literature values and information from watershed managers. So what did I find? Next slide, please. The first is that agricultural sources of phosphorus are dominant. And even though I looked at all these different potential sources, the agricultural sources accounted for more than 90% of all additions for each year of the study. And of this, fertilizer was the largest component, and then livestock manure for this particular watershed. And it's important to note that that fertilizer is largely being applied to corn and soy crops that ultimately go to feed livestock. And this is really a trend that we see nationally as well. And in this watershed, that excess phosphorus has mostly accumulated within the soils of the watershed. I found that there was way more within the watershed soils than there were within the lake bottom or the wetlands. Next slide, please. And given this, if additions of phosphorus to the watershed are not reduced and everything continues in a business as usual situation, it could take over 20 years for the soils in the Green Lake watershed to get back down to an appropriate level for crops because so much is already built up. If there was a more dramatic reduction, like stopping all fertilizer additions, this could happen in less than 3 years, but that's not really realistic. It does show, however, the importance of reducing phosphorus additions. Management efforts can't just be focused on traditional measures like preventing erosion or trapping phosphorus on the landscape, but they also need to work on actually cutting down the supply to begin with. And zooming way out, this is especially important nationally and globally because the phosphorus used in agriculture is a finite resource. Next slide, please. Most of the phosphorus that's used in our agricultural system is mined from phosphate rock in just a few countries in the world. And it won't be able to support continued demand for more food and more people if we keep farming like we currently do. And so this suggests some opportunities, like using legacy phosphorus that's stored in soils as a potentially free source of fertilizer to crops. Opportunities to reduce food waste in the agricultural system, and then also moving towards a system that's more diversified, and one that's not just focused on a few crops that are grown to feed livestock, but one that is also growing more vegetables directly for human consumption and utilizing grazing and a variety of crops to feed animals. Next slide, please. And in the meantime, zooming back into my study area, we also need to be aware that water quality recovery will take time. Since legacy phosphorus accumulated over decades, it will likely continue to act as a source to freshwater bodies for many more decades. And this is something that I found and that is echoed in many other studies. And the presence of legacy phosphorus in watersheds and water bodies will continue to be a management challenge. Phosphorus reductions in a watershed might not directly result in phosphorus reductions to a water body because these historical sources exist. And so there will be delays, and increased precipitation and runoff from climate change could complicate this as well. So active management that focuses on reducing those sources as well as drawing down the stores that are already in the soil will be really important. And for those of us who care about ocean and Great Lakes coastal areas, I think that this is something important to understand as well, that nutrient management, both current and historical, in upstream watersheds can play a really big role in the timing of when we'll actually see improvement for downstream areas. Next slide. So thank you very much for listening. I hope you learned something new, and I look forward to questions at the end.
Wow, thank you, Rachel. Really, really interesting research you've done. So awesome. We'll just move right along here. Suzi Webster is our next speaker, and she is currently the Knauss Fellow she's doing stakeholder engagement and communications, specializing in that rather, in NOAA's Technology and Partnerships Office. So she is a PhD candidate at the University of Maryland Center for Environmental Science, where she researches stakeholder engagement and environmental research and management. Prior to joining NOAA, Suzi worked on a team of science communication professionals at the Integration and Application Network and earned a bachelor's degree in biology and anthropology from the University of Notre Dame. And her title of the presentation here today is Co-Developing and Evaluating a Citizen Science Monitoring Program for Chesapeake Bay Submerged Aquatic Vegetation, which is very exciting. So Suzi, I'll hand it off to you.
Thanks, Caleb. I'm assuming everyone can hear and see. Let me know if not. So again, my name is Suzi Webster. I'm talking about some of my dissertation research, which involved collaboratively developing and evaluating a volunteer monitoring program for the Chesapeake Bay. So my talk today focuses on a volunteer monitoring program, which is a type of citizen science. And broadly, just so we're all on the same page, citizen science refers to research collaborations between scientists and volunteers who partner to answer real-world questions and to learn more about the natural world than either group would be able to on their own. So some of you might know that submerged aquatic vegetation, or SAV, is really important for estuarine ecosystem health. And in the Chesapeake region, where I work, scientists use aerial surveys to create an annual map of SAV beds, and then managers and policymakers use this map to make decisions throughout the watershed. So the map is really valuable as it is now. You can see it on the slide, but it could be even more valuable if it also contained more local scale data on SAV species diversity and other kinds of variables that provide more detail on what's going on with bay health and habitat more broadly. So citizen scientists can help us create this fine scale knowledge. The Chesapeake Bay is home to many volunteer monitoring groups, and a lot of them are very eager to collect data on SAV. So when I was working at University of Maryland Center for Environmental Science as a graduate assistant, the Chesapeake Bay program contracted our group of science communicators to develop a training and certification program for volunteers. So my team's goal was to create a program that provided an educational and engaging experience for volunteers, while also generating useful scientific data and informing restoration efforts and management decisions. So we felt that in order to accomplish this goal, we would need to develop the program with the end users not only in our mind, but also involved. So our team kind of acted as a middleman and invited stakeholders to the table, listened to everyone's priorities and perspectives, and then ultimately synthesized all of that input to create a new monitoring program that meets the needs of everyone involved. So we started this process by reviewing journal articles, and we looked at articles that are discussing citizen science. We looked at different sampling protocols, and then we talked to a bunch of SAV experts in the Chesapeake area. And together, we came up with a list of types of data that would be the most useful for a science and management point of view. And since the main goal of this project was to generate impactful data, it was really important to think about data quality and intended use from the very beginning of the project. We also, of course, talked to leaders of the volunteer monitoring groups, and we gave them lots of opportunities to voice their needs and concerns for the new program. And we also went out into the field with volunteers on several occasions, and we learned from them firsthand about their experience collecting data on SAV. So then we synthesized all this information to create a draft monitoring protocol, and we invited all these stakeholders to a 2-day workshop to field test the protocol and try out the draft data sheet and just share their feedback. So we invited we also invited SAV experts to review the monitoring protocol document. And we used all of this feedback from all of these different people to finalize the monitoring protocol and improve our program materials, and then ultimately develop the training and certification program. And we named the program Chesapeake Bay SAV Watchers. So I'll give you a quick peek at the protocol itself, since I know some of you are environmental scientists and might care about the details. So the program has 2 tiers, which are targeted towards different types of volunteers because we wanted to be as inclusive as we could. And Virginia Institute of Marine Science pulls data from both of these tiers and integrates it onto their map that I showed on the first slide. So tier 1 on the left is our introductory monitoring program, and it's geared towards people who are already recreating on the bay and may be interested in kind of like sporadically participating in gathering SAV data. And these volunteers use an app and they share pictures of SAV and their identifications. And then tier 2 on the right is a little bit more intense. It requires training because it's meant to produce data that's higher quality for management purposes. And it's targeted towards people who are members of formal monitoring groups. So group coordinators choose specific monitoring locations and sampling schedules, and then they send their volunteers out into the field to collect the data and fill out data sheets. And participants collect SAV data as well as other information you can see on the slide about the sampling site that kind of gives more scientific context to the SAV data. So besides developing the protocol itself, we also created a bunch of other products that help volunteers learn about SAV and collect their data and ultimately submit it. So we made a methods manual for each tier. We made a training video series that you can find on YouTube, a pocket guide of SAV species, kind of like a cheat sheet for identifying the different species, a data sheet, of course, and then a corresponding digitization template to help volunteers enter that data onto the computer, and then the train the trainer certification agenda. So the training program is designed for volunteer group coordinators, and it offers a mixture of classroom presentations that teach about SAV and its effect on the bay, a review of the protocol, and then an SAV species identification exercise. And at the end of the training, in order to be certified, the participants complete an assessment to become official SAV Watchers trainers. And they're then certified to train members of their own monitoring groups. So we certified the first cohort of trainers in fall 2019. These are the pictures from that training are on the slide. So the pandemic obviously affected monitoring last year, but this year will be the first sampling season where SAV Watchers is officially used. So the data collected will be useful for individual monitoring groups that want to kind of like keep tabs on the health of their local tributaries, but also valuable for researchers and policymakers and managers. So all of this work was part of one of my chapters of my dissertation, which is on public engagement in Chesapeake Bay environmental science and management. So after developing the program itself, I conducted semi-structured interviews with all the people that were involved to understand their perspectives of the co-development process and of the program itself. The evaluation research is important because all of it is very transferable. So it'll help improve the SAV Watchers program, but more importantly maybe, or at least more broadly, our results can also inform the creation of other citizen science programs. So for my last few minutes, I'll just share a couple of our key results from those interviews. So when people were asked to reflect on their involvement in the process, they were thankful for the opportunity to participate to the extent that they wanted, and they commended the process for being able to involve others with such a wide variety of expertise. And importantly, participants felt really valued, and they felt that they felt a shared sense of ownership for the program after seeing their contributions were actually being used to make improvements. Involving stakeholders as genuine partners throughout this process allowed us to create a scientifically robust monitoring program that people are actually really excited to use. So people are excited to collect the data, and they're also excited to use the data. For anyone who's thinking about collaborating with stakeholders or citizen scientists in the future, we really encourage you to engage these partners early and often. And then next, when stakeholders provided feedback on the program itself, a few key points kept coming up. So first, people really appreciated that the program materials were really clear and kind of a complete package. So they said that the materials were user-friendly, the design elements just kind of made everything feel more inviting and credible, and the extra attention that we paid to science communication just really made people feel more confident that others would want to participate in the program, and also that others would want to trust and use the data. And then second, people said they were eager to feel more connected to the other participants as the program expands. So many suggested that SAV Watchers should maybe host some events or send out periodic updates, just to kind of establish more of a sense of community among the SAV volunteers. So as SAV Watchers grows, its leaders will need to keep the communication channels open so they can make sure people are staying engaged and make sure the program is continuing to meet everyone's needs. And then finally, participants also mentioned that it was really encouraging having the program connected to a few respected and well-known scientific and management partners from its very beginning. So these connections made volunteers just more excited to start collecting the data because they knew that people were valuing their work right off the bat. And likewise, scientists and managers were more eager to incorporate the volunteer collected data into their work because it was kind of affiliated with all these other credible institutions. And the partnerships between all these groups were strengthened as a result of this project, and hopefully they'll continue to deepen in the future. So if you want to learn more about Chesapeake Bay SAV Watchers, you can download all of the program materials from the project website, which is on the slide. And then for more details on the interviews and kind of developing the program, my research side of things, you should keep an eye out for a publication eventually. Hopefully, I hope I'm not jinxing myself by saying that. I'd like to finish by thanking all of the citizen scientists and environmental professionals who had a hand in creating SAV Watchers program and informing my research, as well as my co-authors, my colleagues and mentors at UMCES, and my dissertation committee. And then thanks to, of course, NOAA Central Library and Lunch and Learn Committee for organizing the seminar. And to all of you for your attention. And I'll look forward to the questions.
Yeah, thank you, Suzi, so much. So incredibly interesting, something also incredibly important, citizen science. And man, really, really exciting talks today. I've got a lot of questions, but like you all, I will wait until the end. And again, please continue to type those into the chat box so Lisa can fill them at the end. So just moving right along, last but certainly not least, we have Maya Whalen-Kipp. So she is the Knauss Fellow with the Department of Energy and is serving as the Marine and Energy Interagency Coordinator. She is a recent graduate of Bard College, where she earned her master's in climate and environmental policy. In addition, she also served as a Peace Corps volunteer in Fiji, no big deal, and has a passion for championing the conservation of uncharismatic marine life, though I will debate that sea cucumbers are, I mean, they're kind of charismatic. You got to give it to them. So yeah, I'll hand it off to her, and thank you, Maya.
Okay, thank you. I'm so sorry. I'm struggling all around with the tech. I have too many slides up. Can you see my screen?
I think there it goes. Perfect, right there.
Okay, I'm moving around so much. Got it. Okay, so you can see me and my screen all in one.
Sea cucumbers are ready to go.
Beautiful. Caleb, thank you so much for that intro. I would also agree, sea cucumbers may be the most charismatic invertebrates in coral reef ecosystems. And that's not at all what this talk is about, but I am chock full of sea cucumber facts if you want to discuss it afterwards. But I am here today to discuss my master's thesis, which is on the culturally grounded marine management approaches for sea cucumber conservation in the South Pacific. So as Caleb mentioned, I was a Peace Corps volunteer in Fiji, and I started my research then when I was living on the island of Vanua Levu. And this is a community that was deeply involved with the international export of sea cucumbers before the 2017 complete moratorium on the export and harvesting of the animal due to decreased populations. So sea cucumbers are, let me go to the next slide. Sea cucumbers are ectoderms, and they're most closely related to starfish and sea urchins. However, they do not have the calcium bicarbonate exoskeleton, which enables them to be slightly more resistant to ocean acidification compared to their relatives. Sea cucumbers are ecologically important because of their role in nutrient cycling within the coral reef ecosystems. Their digestive system secretes ammonium and phosphates as they are detritivores digesting dead biological matter within coral reefs. In addition, they also excrete ammonia, which is which increases local pH and alkalinity, which buffers the impacts of ocean acidification for their neighbors as well as themselves. So of course, super important for our coral reefs, especially in the South Pacific, which I'm sure you're at this talk, you don't need to know they are struggling. However, regardless of how cool sea cucumbers are, they are endangered in some capacity. 16 of the most commercially valuable species are listed as endangered or threatened. This is an economic problem as well as an ecological one for South Pacific island communities that are dependent on their trade. So I wanted to better understand if there was a way to manage sea cucumber fisheries that would empower local communities instead of a complete moratorium on their harvest and export. Especially considering that indigenous South Pacific cultures are rooted in marine conservation. In 10 out of the 14 small island nations, 75% or more of the land and marine area is under what is called customary tenure, meaning that it is regulated and managed by tribal governance. One of the most studied cultural practices for marine conservation in the South Pacific is this idea of tambu. And this is a term designation that means something is either too sacred or too dangerous to do. It can apply to a lot of different things, but when applied to fisheries, in practice, it implements a no-take zone or a harvest period or harvest rest period for that designated marine area. So my research question is formally, how can culturally grounded conservation methods and customary marine tenure be utilized in implementing conservation policies, specifically to protect sea cucumbers? Okay, so next slide. To better understand this question, I look at 3 case studies in the South Pacific that all embrace South Pacific Islander culture within their conservation approaches. So I look at a case study in Papua New Guinea, Vanuatu, and Fiji, which I will very briefly overview for the sake of time. It's definitely something I could dive much deeper into. So Papua New Guinea is the top exporter of sea cucumbers in the region. And at this point does not necessarily have a very comprehensive management system for them. So a 2005 study by Sinner et al. On coastal conservation, not necessarily about sea cucumbers, but marine protected areas in general, found that the utilization of the tambu designation, that verbiage indicating a cultural fisheries halt, had a ability to have approximately 40% higher biomass, so it was more successful at conserving the biodiversity compared to unrestricted areas or areas that were not designated with the formal tambu restrictions, more just national level conservation initiatives. In Fiji, which is the second largest exporter of sea cucumbers in the region, there was a very interesting study on the southern island of Kindavu, which is a small-ish island, and you can see on this map the little yellow dots indicate where the villages are, or the districts. Those villages probably have between 100 and 500 people that live in them, yet are independently governed. There was an attempt to implement marine protected areas around all of Kindavu, as this is a very pristine coral reef ecosystem. However, marine protected areas are mostly successful when they are large and cover a large amount of area and have some type of management to make sure that they are actually abided by. However, once this proposal was brought to the community level, there was met with a fair amount of resistance because it would basically lump a bunch of traditional lands together instead of divvying up the area boundaries. So the marine protected areas were redesigned to match the traditional boundaries, which are called e-goli-golis, and you can kind of see that outlined here. This was a much smaller area that was then deemed as protected, which goes contradictory to a lot of conservation science. However, this dramatically increased fishery engagement and enforcement on the local level, which overall produces a more thriving biologically diverse ecosystem. Vanuatu is another Melanesian nation that I was looking at. Vanuatu's Ministry of Fisheries closed sea cucumber harvesting in 2014. For a similar reason, they saw dramatic decreases in overall sea cucumber populations and it having adverse effects on the coastal ecosystem. However, of course, this is a big revenue for these small island nations. So they did an evaluation of supply chain management to better understand how they could efficiently reopen the fisheries in the future. And after surveying many of the local fishing communities to better understand how they could engage in conservation practices, it was identified that the #1 limitation for fishing communities to engage was that they were not getting a large portion of the profits that are revenue from the sea cucumber trade. So as you can see on this graphic here, out of 100% of the profits from sea cucumbers, the fishing communities only receive about 21%. Sea cucumbers on the international market is a very valuable commodity. I've seen records of it going to over $1,000 per pound and probably averages about $150 US dollars per pound. This has attracted people from all over the world to get involved with this industry, but it's also really important that this industry is enabling coastal communities to be empowered financially and culturally. So a couple of policy proposals that could increase the take-home profits for fishing communities would be if we had regional co-ops that standardize prices, minimize the middlemen overall within the sea cucumber trade, educate fishing community members on how to process sea cucumbers to assure higher value, and implement permitting systems to limit foreign companies from harvesting the South Pacific in traditional marine areas. So in summary, my policy recommendations are to utilize specific indigenous vocabulary framework within natural resource management, establish conservation zones within the same geographical area of customary land and sea sovereignty, and develop systems that prioritize the allocation of profits from the sea cucumber industry to local fishing communities. So in conclusion, sea cucumbers are a valuable resource ecologically and economically for fishing communities in the South Pacific. And the reality is that the global demand for sea cucumbers will likely continue to rise. Therefore, it is important that we have comprehensive policy that allows sea cucumber populations to flourish and the industry to grow. And of course, as our case studies showed, empowers South Pacific Islander communities have the social infrastructure to protect vulnerable marine species when indigenous culture is embraced formally on a policy level. So thank you so much, and I'm excited to take some questions.
Wonderful. So I want to thank everyone for those really great presentations, and I encourage the speakers to come back on webcam now. And let me actually take control. There you guys are. Wonderful. So audience, we have about 10 minutes to answer your questions. So please go ahead and type them in the questions chat box in the control panel. Make sure that we know who you're addressing your question to. Otherwise, we'll figure it out. And before we start asking the questions, I also want to remind you that all of the speakers have provided their slides as handouts. So if you're interested in them, please go to the handouts drop-down menu in the control panel and download them before we end the webinar today. So let's see, I'm opening up the questions chat box. And we have some questions, excellent. So this first question is for Sandra, and it asks, for the social cost of carbon, did you perform a sensitivity analysis to different discount rates or even a changing discount rate through time? How might that change marsh management approaches?
Yeah, so I did not do a sensitivity analysis for my study per se. Let me talk a little bit about discount rates, because I think that's something that's kind of an abstract topic for a lot of people, and still something I have a hard time wrapping my head around sometimes. But it is from the economic side of things, and so there's many different discount rates that you could use for the social cost of carbon, and those discount rates change based on projected greenhouse gas emissions and climate change scenarios. And so if you have a low discount rate, like around the 2.5, like I used in my presentation, that kind of advocates for immediate action and investment today on things like our marshes and other ecosystems that'll have a lot of impacts due to climate change. And so these low discount rates basically mean that the future costs of climate change will significantly outweigh present day investments. On the other hand, our high discount rates is something like your 3% or even higher, sometimes 5%, you'll see that in a way advocates for not taking immediate action and saying that investing in these kinds of things today isn't worth it and doesn't make sense. And so these different discount rates obviously have different ethical predicaments regarding the well-being of future generations. There's a lot of debate around which discount rates to use. For my presentation, I chose, so in my thesis, I have all the discount rates and show the impacts that those different discount rates have on our value of our marshes and our sequestration rates across the East Coast. But in my presentations and in my specific graphics and my thesis itself, I focus on the 2.5% discount rate because I personally believe that action right now is necessary and is a valuable investment. So in terms of how that changes your marsh management approaches, if you don't think that marsh management is worth it right now, then when you're doing these types of analyses, you would pick a higher discount rate. I personally don't believe in that, but I hope that answers your question.
Thank you. I appreciate your answer. This next question is for Rachel, and it asks, what specific agricultural conservation practices have been most effective in your study area? Subsurface placement of nutrients, changes in tillage, use of cover crops, etc.
Yeah, I'll say that is a great question. I did not specifically look at the effectiveness of different management practices, and there's still some research underway in that watershed that's looking at that. I will say though that watershed managers have really taken the approach of like, it's best if we just try as many things as we can rather than kind of like waiting to see what's best. So some that have been very common are stream bank restoration, so areas along creeks that are starting to erode, cover cropping, doing improvements to barnyard areas to help them better be able to manage manure, and then also trying to take land out of production and trapping sediment in the landscape as well.
Thank you. Actually, there's another question for you, Rachel. It says, not sure if I missed this during your talk, but how did you pinpoint exactly where the phosphorus came from? For example, phosphorus from fertilizers versus livestock waste.
Yeah, that could be an entire other talk in itself. So I did not go into that in big detail. In the simplest sense, I use literature and then conversations with watershed managers to figure out what the largest sources were, and then use basically whatever available data I could find, whether that was county scale information or information that the counties had collected themselves to try to estimate that. I'd be happy to follow up though with that person with an email though if they have more questions.
Thank you. Yeah, we do pass along these messages to our speakers, so rest assured she will have your email. I want to encourage people to continue to ask some questions. We have about 5 more minutes for them. And while we wait for some questions to come in, I just want to remind everybody that we did record this presentation, and we encourage you to share it with others who might be interested in any of the 4 presentation topics. I'm going to upload the recording to the NOAA Central Library YouTube channel sometime this afternoon, probably in about 2 or 3 hours. Meanwhile, Also, I wanted to encourage the speakers, if you have any questions for each other, by all means, go ahead and ask them and right now, and or if not, that's fine as well. And I also want to encourage people to use the library. I saw a number of fantastic articles that were cited in your presentations, and we can access all of them. So please contact NOAA Central Library if you're interested in any of the citations that any of the speakers today brought up. So I'm going to wait another second to see if anyone has any questions, but if not, I want to let Caleb, add some last comments if he has any.
Yeah, thank you. I actually have a question for Maya. I was just curious what what was the most difficult or challenging aspect of working with the community down there as far as coming to a consensus and looking at management practices with the little critters.
Yeah, definitely. So something I failed to mention during my presentation is that sea cucumbers are not consumed locally in Fiji or anywhere in the South Pacific, really. So understanding the ecological value of them, outside of that, they're not used for food. They're used for food mostly in like Asia or East Asia. So embracing that side. But honestly, so much of the South Pacific culture, they love their, South Pacific people love South Pacific culture. And when you're starting to talk about integrating indigenous language into policy, it's welcomed with open arms. So I found a lot of people wanting to talk about that. It's honestly just hard to get people to focus on one topic when you're talking to them about indigenous culture.
Yeah, no, that's awesome. So it seems like just demand is pretty high as the driving factor there. So with that, I suppose, do you see any more questions, Lisa, or do we have any more coming
Yeah,
in?
I did. I got one for Suzi. So Suzi, the question asked, do you see a growing acceptance of citizen science done through these sorts of organized trainings as being more accepted across the broader scientific community and government regulation?
I do. I think that, in recent years, different major organizations like the EPA and NOAA have put together citizen science reports, kind of reporting on all of their stance as an agency, what they think of citizen science, and it's very accepting. So that's kind of encouraging like state governments and more local scale governments to accept that data as well. And also people are just more so seeing the value of getting different types of people involved in science discourse. So into the conversation, invested in their local environments more in a scientific way. So I think it's definitely becoming more accepted by all levels, from the federal government to local communities.
Excellent, thank you. Well, I think that's our last question for today. So I want to give everybody a chance to say anything, last words if you have them. Nope. Awesome. Okay, well, then I'd like to conclude by thanking all of you, our speakers, for sharing your research with us, as well as Caleb for doing an excellent job with the moderation and the introductions, and the Knauss Fellows Webinar Committee for organizing this series. Please share the recording. Again, the presentations were fabulous, and I know there are many people at NOAA who would want to hear them. I'll upload them later today. NOAA Central Library is very proud to host presentations like today's that feature the work of the Knauss Fellows and the NOAA community, and we hope you will join us again. The next Knauss Lunch and Learn webinar will be on June 17th at noon Eastern Central Time. So be well all, and thank you so much for joining us.
Thank you.
Thank you.
Thank you.